Hello and welcome back. In today's video, I'm going to be going over the 2025 AP Physics C Mechanics free response questions for Form J. If you have any questions, let me know in the comment section down below. Otherwise, let's get started with question 1. And for part A, we're going to be drawing momentum vectors. You can see that block 1 has a momentum of 2 mv and has an arrow to the right with 2 blocks. So that means for a momentum of negative 6 mv, we have 6 blocks to the left. So 1, 2, 3, 4, 5, 6. And after the collision, what is our momentum going to be? It's actually going to be the same as before the collision as well. Remember, conservation of momentum. There is no external force being applied here. So 2 mv minus 6 mv gives us negative 4 mv. So 1, 2, 3, 4. And that's going to be the same over here. 1, 2, 3, 4. That's part 1. Let's do part 2 now. During a time interval, a force is applied on block 2 by block 1 along the x direction as a function of t that's modeled by this. And we actually have to solve for F max. Well, how are we going to do this? I'm seeing force as a function of time and I'm seeing momentum. That just means that we're going to be doing impulse. But what's impulse? Impulse is the change in momentum and we're focusing on block 2 specifically. But how can we find the impulse for block 2? In order to do this, we have to find the ending velocity of our 2-block system. We have a starting momentum of our 2-block system of negative 4 mvo, and that's going to be equal to 7m, because m plus 6m, they combine together to make 7m vf. So if we divide this to the other side, we just divide this, we get an ending velocity of negative 4 over 7 times v naught. So how are we going to be using this? I said we're looking at impulse. So I'm just going to draw it on decimals over here. So we have an ending velocity of negative 4 over 7, and we have a starting velocity of negative 1. So it's going to be minus negative 1, because remember, it was moving a velocity of v to the left. And so this gives us, and this is actually the same as 3 over 7. So this is telling us that the change in velocity is going to be 3 over 7, multiplied by our mass to get impulse, m is going to be 6. This is going to give us 18 over 7. So we know our impulse is going to be equal to 18 over 7. But what do we set this equal to? That's actually going to be 18m over mv over 7. But what do we set this equal to? We're going to be integrating this force function with respect to time from 0 to tc. So it's equal to the integral of 0 to, I'm going to say c, but it's going to be tc. We're going to integrate the force function being f max times sine of a t dt. Now, force isn't changing. The F max variable, force is changing, but the F max variable isn't. So we can safely bring that outside. And now we just have to find the antiderivative of sine A of t. Well, the antiderivative of sine is going to be negative cosine. But since we have an a in here, we have to do the reverse chain rule. Meaning that this is going to be equal to F times negative cosine of AT. But now we have to plug in our bounds. And also you have to divide by a as per the reverse chain rule. So now we have to plug in our bounds, which are 0 and tc. So first you're going to plug in tc. We're going to leave the f outside. You don't need this. We're going to leave the f outside. So first we're going to plug in tc, giving us negative cosine ac divided by a. And then we're going to be using the 0. So subtracting negative cosine of 0 is going to be 1, so minus 1 over a. And this actually adds, again, we don't need this. This adds to give us negative cosine AC minus 1 all divided by A. So this is going to be equal to the impulse over here. So this will, and this we're actually multiplying by F max, so times F is equal to 18 mv divided by 7. So all you have to do now is multiply A to both sides, so mv A. And then you're just going to divide by negative cosine A of c minus 1. And actually it's going to be a plus 1 because we're subtracting a negative. And so now you could just say 1 minus cosine AC. So we're just going to divide this to the other side, like so. 1 minus cosine A times, this is TC, now we can write that. And this is the function for your maximum force. So we're just going to write that over here again. Your max force is equal to 18 times your mass times your velocity times the value of A divided by 7 times 1 minus cosine times a times t of c. And that is the answer for part 2, deriving the expression for f max. Now that we've done that, let's do part B. I'm going to move this up here. Part B. Consider a new scenario where block 1 initially slides in the plus x direction with a new constant speed v1, and block 2 again initially slides in the negative x direction with constant speed vo. They collide, and the ending velocity is going to be vo. Derive an expression for v1 in terms of vo. Well, again, we're just going to be doing conservation of momentum. So we're seeing that block 1 is mass m, so m times v1 plus, we have block 2 slides in the negative x direction with constant speed vo, so minus 6m vo is equal to what? Let's see, they collide and stick together, and there's a constant velocity vo again. So it's going to be equal to 7m vo. Well, this is actually rather easy to solve. We just have to add 6m vo to the other side, giving us mv1 is equal to 13m vo. And then you just divide the m, giving us v1 is equal to 13 vo. And there's your answer. That's the expression for v1. Now we've done part B, let's actually move on to question 2 now. I'm going to clear this up here. Now, question 2. In scenario 1, a system is comprised of 2 springs, A and B, and there's a block of mass m in the middle here, and friction between the block and the surface is negligible. Okay, and each spring is attached to a fixed wall, and we have spring A with a constant k, but spring B has spring constant of 2k, and these are the relaxed lengths, meaning there's no energy stored in the spring. Then, the block is moved to position x equals x1 and held at rest. Okay, so what do we have to do here? We have to fill in this energy bar chart, and UA represents the elastic potential energy of spring A, UB represents the elastic potential energy of spring B, and K block represents the kinetic energy. And we have to draw on the shaded bars. Well, here's the easiest one. K block is being held at rest. There is no kinetic energy. So this is just going to be a flat 0. But next is UA and UB. So when we have UA and UB, we need to think about what we have. Remember, spring B has twice the spring constant of spring A. And if we look at our equation sheet over here, we can find the energy for a spring, and that's over here, 1 over 2 kx squared. The k isn't being squared or anything, so if I increase my value of k by 5 times, the energy is 5 times greater. And in this scenario, both of them are being compressed by the same x. This is being spring A is being extended by x1, spring B is being compressed by x1. That means that spring B is going to have twice the energy stored as spring A. So you can draw, let's say, 4 blocks here and 2 here, or 2 here and 1 here. It just has to be relatively proportional. So let's fill in 2 bars like this, and 1 bar like that. There we go, that's part A. Now part B. The block is released from rest at x equals x1 and begins to oscillate. Derive an expression for the speed v of the block as it passes through x equals 1/2 x1. Express your answer in terms of these variables. Now, how are we going to do this? We're going to be using conservation of energy. So what are we starting with? When we start, we have no kinetic energy, but we have some potential energy, spring potential energy. And that's going to be 0.5 times k times x1 squared. So I'm just going to write x squared. And then we're going to be adding 0.5 times 2k. So that just becomes k times x squared again. And remember, I'm saying x equals x1. And we have no kinetic energy. Actually, for clarity, I'm just going to write x1 squared like this. But this is going to be equal to some kinetic energy. So that's going to be 0.5 mv squared plus our new potential energies. And our new potential energies are going to be 0.5 times k. But what's the spring compression? We're being told it's going to be x is equal to 1/2 of x1. So it's going to be moved all the way over here. So the compression distance is actually going to be 1/2 of, well, x1. And remember, this term is being squared, so it's actually going to be 1/4. This is going to be x1 squared divided by 4 plus 0.5 times 2k, that just becomes k, times, let's put this in parentheses, x1 squared divided by 4 again. So let's extend this out like this. Well, now we can see all we have to do. We just want to isolate this term over here. So let's do that. So if we add these together, we're going to get 1.5 kx squared, k1x squared, so 1.5. And let's add these together. These are divided by 4, so remember that. So this is going to be 1.5, but divided by 4. So 1.5, add 1.5 here, and remove this. Now all we have to do is subtract this to this side. But I have a 4 in the denominator that I really don't want. So let's multiply both sides by 4, so this becomes a 2, and this becomes a 6. Good. Now we can divide both sides. We can not divide, we can subtract both sides. And this gives us 4.5 x1 squared times k, 4.5 k1x squared, is equal to 2mv squared. Well, what's 4.5? 4.5 is actually 9 over 2. And so let's divide by 2 again, giving us 9 over 4 actually. 9 over 4. So what's our final answer going to be? Remember, we're looking for velocity. So we're going to divide by m as well. So remember, this is 9 over, let's actually rewrite this. So this is 9 over this, divided by 4m now. And what's our final thing going to be? We're taking a square root. And I'm just going to write it here again. So we have 9kx squared divided by 4m is equal to v squared. Now remember, x in this scenario, now that we've substituted everything, is still going to be x1. So now we just have to take the square root. So I'm going to square root both sides. And once I square root both sides, this is what's going to happen. The square root of 9 over 4 is going to be equal to 3 over 2, so we can take that out of the square root. This is supposed to be to the 1/2 power, by the way, because that's the square root. The square root of 9 over 4 is going to be 3 over 2. We can pull out the x squared and make that an x. And we just have the rest stored in the fraction. So we have k divided by m. And that's the value for your velocity. Your velocity at this point is going to be equal to 3 over 2, we're going to say 1.5, times x1 times the square root of k divided by m. And that's your answer for part B. Now let's move on to part C. In scenario 1, the block oscillates with period t, so that's this scenario up here. Yeah. So it's oscillates with period t, and the position x of the block in scenario 1 as a function of time is shown here. Great. What do we have to do now? We have to sketch a graph of the kinetic energy k of the block as a function of t for scenario 2. And what's scenario 2? It's the block spring system, so our k and 2k springs, on a new surface with friction between the block and the new surface. And the block is moved to the same position and released from rest. So how's our kinetic energy graph going to look like? Well, let's just look back here for a second. We can notice that this function over here looks like a cosine graph. So if I took the derivative, that means the velocity function is going to be a sine graph. And since kinetic energy is 1 over 2 mv squared, our kinetic energy graph is going to resemble a sine squared graph. But how do I know when my peaks appear? Here there's no velocity, here there's no velocity, here there's no velocity. So that means the kinetic energy here and here and here are all 0. That means in between here there are going to be peaks. But remember, we're being told that there's friction now. So that means through every single oscillation that happens, the kinetic energy keeps decreasing. So this is how we're going to draw our graph. So it's going to start off like that, and we can let's actually graph a sine squared graph so you can know what it looks like. There we go. So this is actually what you want to try and draw. Let's hide all of this. You want to try and draw this. So let's start doing that. So we're going to draw something that goes up like this. And we can actually draw the peak to be higher. So let's say it goes like this. Right? That's your first peak. But remember, there's friction now. So your next peak is actually going to be a bit less. And then it goes to be a bit less. And I think you can see the pattern now. It just keeps gradually getting less and less and less. And does it match up? At 3t, 5 over 2t, we all have no kinetic energy. That makes sense. As you can see, it just gets less and less and less and less and less. That's what we want. So now we're on to part 3. In scenario 3, you're replacing the block with a much larger block, and the coefficient of kinetic friction between the new block and surface is the same as scenario 2. And you're moving it to x1, the same as we did in the previous scenarios, and we're releasing it from rest. And we have to see how this new graph of kinetic energy is going to change. So what's one thing that's going to change? Well, I think that the peaks are actually going to drop much greater. And this is why. Friction is the reason that these peaks are dropping, and friction, well, kinetic friction is going to be equal to your normal force, which is mg, times your coefficient. Well, now our mass is much greater, so that means the friction force is going to be much greater through each oscillation. So, one feature of the graph of K, let's expand this. In scenario 3, remember it's as a function of t, in scenario 3 is that the peaks of the graph, and it's going to be the local maximums, will decrease in height much faster when compared to scenario 2, since the increased friction due to the greater mass results in a quicker loss of kinetic energy. And all you have to say is something like this. And there we go, we've answered part D. Now we're going to be doing question 3. And this is the experiment part of the exam. So in this question, we have a block and box set up over here, and it rotates from a certain height. And once it reaches the stopper, which is a vertical position, the rod doesn't move anymore, but the block is free to exit. So it exits along this surface here. So what do we have to do? Students are asked to experimentally determine the acceleration due to gravity using a linear graph. So we have to describe an experimental procedure that the students can do using what they have here, a meter stick and motion sensor, to collect data and then determine g. So let's actually write the method. So A, let's see, so number 1, set the box and block setup to a certain height. And this is a height that's determined by the students, any random height. Next, what you want to do is set the motion sensor parallel to the floor in front of where the box will be exiting the block. No, in front of where the block will be exiting the box. Number 3, record the height at which the box and block setup was released. And then what we have to do is record the maximum velocity recorded by the motion sensor. Now, since we're assuming there's no friction, the velocity should be constant until it, hits the motion sensor, because it's only detecting once the block actually comes in front of it. So record the maximum velocity, and 5, repeat steps 1 to 4 for varying heights. Well, there we go, and let's see part B. How can we actually use this data? So describe how the data collected in part A can be graphed and how that graph would be analyzed to determine the value of g. Well, in order to do this, we're going to be using the conservation of energy. Remember, the mass of the rod is negligible, so nothing to account for with rotational inertia. We just have a block with energy mgh, and at the end it has a velocity, which is recorded, of 1/2 mv squared. But our mass doesn't even matter here, because the m cancels out, giving us gh equals 1/2 v squared, or v squared equals 2gh. Or you can write that as v squared equals 2gh. Now we don't want to plug this in. So what are we going to do with this information? Well, we want to have a linear graph in which the slope is equal to g, or we can use it to find g. But what we can do is, as per the equation, v squared equals 2gh, and you would show how you actually got this equation, we can graph velocity squared against the height at which the box was released. The slope of this graph will be equal to 2g. Then we just have to divide the slope of the graph by 2 to get the value of g. And that's your answer. We have v squared equals 2gh, so this is our y and h is our x, and our slope is 2g, so you divide it by 2 to get the value of g alone. Now on to part C. So we're repeating this experiment, but it's no longer a smooth surface, it's actually rough. We have a value of mu. The coefficient of kinetic friction between the block and the new surface is mu. And the block-box system is pulled so that the center of mass is displaced various distances h, and we measure the max position it reaches. And we're trying to find mu. So how are we going to use x max at all? Well, remember, x max is when the block stops moving. In our previous scenario, the block could move freely. So how are we going to use this information? Well, remember, the second it exits the box, all of that potential energy gets converted into kinetic energy. But at the end, there's no kinetic energy, meaning that some work was done on the system. So mgh minus w, the work, equals 0. So, what was our work? Our work was, well, the force of friction times x, because work is force times the distance that the force is applied over. And x max is the distance that the block traveled. So we're going to write x, and then we're going to write the force of friction formula. And what's that? That's normal force times mu, and normal force as well, mg. So mg times mu. But if we rearrange this, and again, we don't want this, if we rearrange it, then we get that mgh is equal to x times mgu. You cancel out the mg's, and look what you get. Height is equal to x times mu. And that's literally a linear graph. You don't need to do any calculations with the slope. The slope is mu. So let's see what we're graphing. We're going to be graphing h of m, hm being meters on the y-axis, and x max in meters being on the x-axis. And I don't really need to draw the graph that well. I believe you can do this, but I'm going to do the basics. So you want to make sure you have x max and write the units. You want a 0, and then you want the height that you released it at. So let's solve this. We're going to put in 0.3, 0.45, 0.6, 0.9, so height. We're just going to write 0.9 here, a 0.45 here. And we're just going to estimate the rest. What do we have for x? We're going to put a 2.3 here. This is then a 1.15. And let's just plot the points. So we have 0.3. That's going to be somewhere here. And all you have to know is that it's just going to be somewhat linear. Let's just say it looks like that. I'm not actually going to plot the points for this video. I'm just going to go through the calculations. So now we're going to find an experimental value for mu. So let's just find the average slope. So during the test, you would pick the points that are closest to match your best fit line, but I'm just going to use 0.9 and 0.3. So we have 0.9 minus 0.3. Let's write that here. 0.9 minus 0.3 divided by 2.3 minus 0.67. 0.76. So 2.3 minus 0.76. And I have it on my calculator. This is equal to 0.390. The most important thing is that you draw your best fit line and you pick 2 points that are close to your best fit line for the calculation. This would be my final answer. Now on to question 4. So question 4, you have a disc and a ring going up this ramp, and it says the ring travels a greater distance along the ramp than the disc. Okay. And let's look at the first question, part A. While the disc and ring are rolling without slipping, the magnitudes of static frictional force exerted are Fd and Fr. And you need to indicate which is greater, less than, or equal to. Is Fd the same, less, or greater? And justify your answer using qualitative reasoning, so no equations. So how can we answer this? Well, let's just see what we have here. They're the same mass, okay, they're the same radius. They're both going on the exact same ramp, and wait, let's look at this. The same material. They're going up a ramp with the exact same material and exact same mass. The formula for static friction is equal to your normal force, so I'm going to write Fn times, so let's just write Ff for force of friction. Force of friction is equal to your normal force times mu. And mu is the coefficient of friction between two different materials. But look at this. We have the exact same material for both the rings. So at the point of contact, we have the same materials and we have the same mass, meaning our normal force is going to be the exact same. Therefore, your force of friction is going to be the exact same for both. Fd equals Fr. Let's cancel these out. And my reasoning is going to be here. Since both the disc and the ring have the exact same mass and materials, the force of friction applied when they both roll onto the exact same ramp will be the same. Because remember, all we care about is the normal force and mu. And normal force is going to be the same for both since they have the same mass. Now on to question B, a derivation. A cylinder with mass m, radius r, and rotational inertia I about its central axis. So that's what it has. and it rolls without slipping up a ramp. So that would be like this, it's rolling up. And derive an expression for the magnitude of the static frictional force exerted on the cylinder by the ramp. Express your answer in terms of m, r, I, and theta and physical constants. Begin your derivation by writing a fundamental physics principle. So, this might seem tricky at first, but then let's focus on this part right here. Where is it? It rolls without slipping. When an object rolls without slipping, it obeys this equation. It should be right around here. It's right here. Your tangential acceleration, so your linear acceleration, is equal to your radius times your angular acceleration. That's what we care about here. So A is equal to r alpha. Now, how can we use this? Let's think about what our linear acceleration is. So I can draw my free body diagram here. You have the force of gravity downwards, which splits up into these components. But then, where's your force of friction? Is it down or up? Well, notice, the cylinder here actually slows down and it rolls all the way up. So I'm going to be putting a force of friction up here. It's moving up and slowing down. So gravity is down here, and our force of static friction is pointing upwards. So let's look at the forces that are actually impacting the linear acceleration. We have gravity and friction. So let's write that down. A is equal to, not alpha, A is equal to, and let's define down as being positive here. So it's going to be equal to mg sine theta. So mg sine theta, where m is the mass of the cylinder. Mg sine theta of, and 0 is going to be our theta, minus your force of friction. Let's just leave everything in terms of F, force of friction. That'll be correct because we're having gravity down here minus your force of friction here. But this is actually equal to ma because F equals ma. So we're going to divide everything by m, giving us, we can just write it like this for now. A is equal to mg sine theta minus ff, all of that divided by the mass. But now let's focus on what our angular acceleration is. So tau, and that's force times radius, so let's look at it over here. Tau is equal to your radius times your force. But also, tau is equal to I alpha. So tau is equal to force of friction because that's the only thing causing a torque here. Gravity doesn't cause a torque. So your force of friction times the radius. But tau is also equal to your moment of inertia times angular acceleration. Now I'm going to write a capital A for this. So what does that mean? That means if we divide this by I, the moment of inertia, we get this. We get the angular acceleration is equal to the force of friction times the radius divided by the moment of inertia. So now that you have your formula for angular acceleration and you have the tangential acceleration formula, we can actually solve this, and we're going to be using Desmos just to write everything. So we have mg sine theta, I'm going to write that like this, mg sine theta minus F, which is our force of friction, all divided by m. Now this is going to be equal to negative r, because our angular acceleration is negative, so negative r squared, because we have an r over here, times F divided by I. Now, how can we actually solve this from now? So first, let's simplify things. We're going to do F over m, and we're going to cancel out the m over here. And this is still a small m. What you want to do is you want to isolate the force of friction on one side. So we're going to add F over m here, plus F over m. Let's delete these parentheses. Now what you're going to do is you're going to isolate F again. So again, let's delete this. And your right-hand side is going to look like this. F times negative r squared over I, negative r squared over I, plus 1 over m. And this is going to be equal to g sine theta. And now the final part. We just have to divide everything to the other side, giving us F, the force of friction, is equal to g sine theta divided by 1 over m minus r squared over I. And I'm just going to quickly explain again why we did this. You have your tangential acceleration, the force of gravity moving it down the hill, minus your force of friction, all divided by mass to get acceleration. You have your torque here by the force of friction times radius. divided by our inertia to get angular acceleration, and we plugged it into this formula. Then we divided mg sine theta by m to get g sine theta minus ff over m. As you can see over here, we isolated the force of frictions, then we simply solved for the force of friction. And that's the answer for B. So I'm just going to write it quickly here. F equals g sine theta divided by 1 over m minus r squared over I. Well, that's the force of friction for part B. And now we're on the final part of the exam, part C. In a different scenario, the centers of mass of the original disk and ring each have the same initial speed v as they did in the original scenario, but this old ramp is replaced by a new ramp, on which the disk and ring actually slip as they roll up the new ramp. Indicate whether the magnitude of the kinetic frictional force experienced by the disk is actually different than the ring. Now, I'm going to be using the same logic as I did in part A. The ring and disk still have the same material, and again, they're going up the same ramp. And your kinetic frictional force cares about the normal force. Same mass, same material, same frictional force. So, the forces of kinetic friction experienced are the same. That's right, are the same. Both objects have the same mass, therefore have the same normal force. Both objects, normal force experienced. Both objects are also made of the same material, so they have the same coefficient of kinetic friction with the new ramp. Therefore, the forces of kinetic friction experienced are the same. Anyways, that's the entirety of AP Physics 2025 for your response questions for Form J. AP Physics C Mechanics. If you have any questions, let me know in the comment section down below. Otherwise, goodbye.